All right, objective 4, our last objective for Algebra 2B, probability and statistics. Now, those two words have a lot of stuff involved with them. Okay, so we kind of have a lot to cover with this lesson. None of it's super crazy tough, but yeah, like we said, kind of a lot to cover. So let's rock and roll here. Now, the first thing we're going to talk about related to probability is what's called counting principles. Okay, counting the number of ways events can take place. So for our first few examples, let's use this. Let's say Mr. Bailey's closet contains 11 dress shirts, 5 pairs of pants, and 7 ties. We want to look at in how many ways can Mr. Bailey make an outfit with a shirt, pants, and a tie. Okay, assuming that all stuff looks equally good together. Okay, it all looks good to me. For that, we're going to utilize the fundamental counting principle, which says that the number of possible outcomes of multiple events is the product of the number of outcomes of each individual event. Okay, so for example, if we think of picking a shirt, picking a pair of pants, and picking a tie as each individual events, what we have then are kind of 3 slots to fill, 3 things to do. Pick a shirt, pick pants, and pick a tie. And how many ways can we do that? Well, there's 11 shirts, so that'll be 11 times 5 pairs of pants, okay, times 7 ties. All right, just multiply those through. When I do that, I end up with 385. Okay, so with that kind of modest wardrobe there, we end up with 385 different outfits. Again, assuming everything looks equally as good together. Next thing we're going to talk about is the idea of a permutation. I'm going to say that's an arrangement of objects in a particular order. So for this next problem, we're going to look at my dress shirts and just putting them in order, okay, on hangers in my closet. And I'm going to say there are n factorial permutations of a set of n objects. Okay, so as in n factorial, which means n, the number n, times n minus 1, so 1 less, times n minus 2, 2 less, times n minus 3 times n minus 4, times 3 times 2 times 1. Okay, so in how many ways can Mr. Bailey arrange his 11 dress shirts on hangers in a closet? Well, that would be just 11 factorial. If I want to put all those shirts in order, okay, so that I have 11 days in a row to wear them, okay, which we said is equal to 11 times 10 times 9 times 8, times 3 times 2 times 1. And relating that back to our fundamental counting principle, how many different ways could I put a first shirt on a hanger? Okay, well, there's 11 ways to do that. Now for the second hanger then, once I've already hung one shirt, there would be 10 ways to do the next one. Okay, times 9 ways to hang the next shirt, times 8 ways to hang the next shirt, So what I could do is I could plug that into the calculator like this. Or we could also look for the factorial operation. If I pull my calculator out, what I'll do is I'll go 11, and then for the factorial key, I'll go math, scroll over to prob, as in probability and statistics. Scroll down to option 4, there's my exclamation point, there's my factorial. 11 factorial, hit enter, and I end up with, holy smokes, 399. All right, 16800. So what is that? All right, 39 million different permutations of shirts. Okay, different ways I could arrange those shirts on a hanger. All right, so I don't need to worry about repeating myself. I could always come up with a different 11-day option. Next thing we're going to look at is permutations of n objects taken r at a time. So as in this case, let's say I have my 11 dress shirts, but I only want to pick 5 of them to wear for the week. Okay, how many different orders could I come up with, as in 1 for Monday, 1 for Tuesday, 1 for Wednesday, and so on? Well, that's going to be given by this formula, n factorial, divided by n minus r factorial. And basically what this n minus r factorial does is it divides out the ways that I'm not going to use the rest of the objects. Okay, so we could use this formula here, or we can type in it as n permutate r. We'll show you where to find that in the calculator. Okay, so back to the situation. In how many ways can Mr. Bailey pick 5 shirts to wear for the work week? Okay, so as in I want to lay my shirts out or arrange them on hangers on Sunday, so I'm set to go for the week. Well, we just write that as, that'd be, we'd say 11P5. So I have 11 shirts. I'm picking 5 of them to permutate, which is the same thing as just 11 times 10 times 9 times 8 times 7. Okay, how many ways could I fill, in other words, this 5 days of the week? Now, 2 options. I could just punch it in the way I see it here. I could plug it into a fraction like this, or I could use the calculator, where if I hit, once again, math, prob, option 2 is my NPR, N permutate R. And I can just fill in those 2 slots. I have 11 objects or 11 shirts, and I'm picking 5 of them. Hit enter, and I end up with 55,000, or what is that? Yep, 55,440. Which we'd expect to be less than we had for our last problem, just because we're not arranging those last 6 shirts. We're only worried about the first 5. The next thing we're going to talk about is the idea of a combination. I'm going to say a combination is in a selection in which order does not matter. Okay, so for example, in how many ways can Mr. Bailey choose 5 shirts to throw in a bag and take on a trip? Now, the difference between this problem and our last one where we ordered things for Monday, Tuesday, Wednesday, Thursday, Friday is if I'm just throwing shirts into a bag to take with me, it really doesn't matter which one I throw in first, which one I throw in last. Okay, when I get to my destination, I've got all the shirts. So I'd say this is a combination where order doesn't matter. Okay, the number of combinations of n objects taken r at a time is given by this, n factorial divided by the n minus r factorial, with an additional division by r factorial, which is essentially just going to divide out the number of ways I could order what I'm taking with me, what I have in that group. Okay, we could write that as NCR, n combination r. Okay, rather than just plugging this in, we'll probably always use the shortcut on the calculator for this one. So here, once again, I have my 11 shirts, and I'm going to choose 5 of them. And again, we can just go to our calculator, math, scroll over to prob, and option 3 is N, choose R. And filling those in, again, we have 11 shirts. We're going to choose a combination of 5 of them. And notice there's significantly less combinations than there are permutations. And again, the reason for that is order doesn't matter with a combination. If I have red, green, blue, white, black, let's say purple, for combinations, we're going to count that as the same thing as if I said purple, green, blue, black, red. Okay, all those different combinations work out the same. So when it comes time to do permutation and combination problems, really our calculator is doing all the hard work for us. We just have to plug things in the formula. The whole trick is going to be deciding whether or not we're talking about a permutation or a combination problem. And I've got a great example to help you keep the two separate. Let's say there are 5 candidates running for office. In how many ways can you pick? Okay, the first one, a president, vice president, secretary. For part 3, a 3-person committee. Okay, when we're talking about the president problem, okay, think P, think permutation. Okay, for this case, it matters which one comes first, which one's the president, which one's the vice president, which one's the secretary. Okay, there's going to be different responsibilities and powers for them. So this problem would be the 5 P3 permutations, whereas for committee C, think combination. If you're on the committee, you're on the committee. It doesn't matter if you're the first person or the last person on it. That's why I'd say this would be a 5C3. All right, so math, prob, P for the president problem, 5 P3 is going to give us a 60. And then for the committee problem, same thing, math, Let's go over to prob option 3, C, 5, C3. Once again, we'll see there's significantly less. Okay, again, a great set of examples to help you keep the difference between permutation and combination kind of separate in your brain. The next thing we're going to take a look at is calculating probabilities. Okay, we'll say that if E is an event in a situation where all outcomes are equally likely to occur, then the probability that E will occur is, we could say, P of E, as in the probability of E occurring is the number of ways that E can occur divided by the total number of possible outcomes. All right, so the ways what we want to have happen can happen, divided by all the ways things can happen. Okay, a few things about probabilities. They're always going to be between 0 and 1. Okay, so you can't have a negative probability. You can't have a probability higher than 1. And then also you can express them as fractions, decimals, and percents. Okay, we'll look at some different ways, and we'll also talk about which one makes sense as we go through some different answers we get. So let's take a look at finding some probabilities. For problem 6, we have a pair of dice is rolled and add together. Okay, find each probability. And what I have on the right side here is a graphic representing all the different possible outcomes. So for example, let's say I roll a 4 on one die and a 3 on the other. Okay, put those together, that gives me a 7. Okay, here I want to know what's the probability of getting a 7. We could write that as P of 7. And that's going to be equal to, for a fraction, and our numerator is going to be the number of ways I can get that 7 I'm looking for. Let's take a look. There are 1, 2, 3, 4, 5, 6 7s. All right, my denominator is going to be the total possibilities, so that's going to be the number of different ways that anything can happen on the dice. Well, for that, there's 6 ways we can roll the first die, times 6 ways we can roll the second die. Okay, counting principle, 6 times 6 is going to give us 36. Okay, so in other words, we can reduce that down to 1/6. So we can express that probability as a fraction. Or we could make a decimal out of it. If I divide 1 by 6, I get a 0.17 repeating. All right, or we could multiply that by 10 and say 17.7%. Sorry, 16.7%. Okay, 3 different ways to express the probability. Basically, if it's a nice fraction, we'll just leave it like that. All right, B, probability of getting an even number. So we could say P of even. Now my guess for that would be a half. Okay, half evens, half odds. I'm not 100% sure just with the dice here. Let's take a look. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 evens out of 36 possibilities once again. Okay, 18 over 36 is in fact 1/2. Okay, so yep, we get that 1/2 here. All right, moving on. P of getting a 1. So we could say P of 1. Now on the dice here, notice there are 0 different ways I can end up with a 1. So it'd be 0 out of 36, or in other words, just a 0. Okay, so here's an example of something that has a 0 probability or a 0% chance of happening. If it's not even an option, okay, 0 divided by anything will give us a 0. All right, then last one here, just another example. Probability of getting a prime, so we could say P of prime. Okay, prime numbers are numbers that are only divisible by 1 in themselves. So for example, we've got 2, 3 is prime, 4 is not prime, 5s will be, 6 is not, 7s will be, 8s are not primes, 9s are not primes, 10s are not primes, but 11s are. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 out of 36. Divide both by 3, that'd give me a 5 out of 12. So we'd say 5/12 of the time we'll get a prime. Next thing we're going to talk about are probability of multiple events taking place. And first we'll talk about the AND case where we multiply. First thing we need to deal with is independent events. Those are just events in which the occurrence of one does not affect the other. All right, and if A and B are independent events, then the probability of A and B happening is just the probability of A times the probability of B. Okay, so when we see AND, think multiply. And the trick is we're going to have to determine if the events are independent. If so, it's a pretty easy problem, or else we'll have to make some adjustments. We'll show you how to do that here. All right, so let's say that a bag contains 7 red, 5 blue, 6 yellow, and 4 green marbles. We want to find each probability. First one is the probability of pulling out a red, replacing it, and then pulling out a blue. So we could write that as P of, I'll just say R and B, as in the probability of getting a red and then a blue. Okay, since we're replacing here, these two events are going to be independent of each other. Okay, I pull one out, put it back. Okay, my chances are going to be the same. So there are 7 reds out of a total of, let's see here, we've got 10, 15, 22 possibilities. All right, times we're replacing, probability of getting a blue, there are 5 blues out of the 22 possibilities. All right, we can just multiply those fractions together. 7 divided by 22 times 5 divided by 22. And when I do that, fraction is going to be pretty ugly, so we'll just write it as a decimal. I can write that as a 0.07 for a probability. All right, B, probability of getting a red, holding onto it, and then pulling out another red. Okay, in this case, I'm going to say that these two events are not independent. Okay, because since I'm going to hold on to my first marble, the probabilities or the chances for my second marble are going to depend on what I got for the first one. So we could write this as P of R and R. And since these events are not independent, the way I'm going to write this, I'm going to say it's the probability of getting a red, okay, times the probability prime, we'll say P prime of getting a red. In other words, we have to adjust this second probability based on what we get for the first one. Okay, so for the first red will be the same, just 7 over 22. And now the chances I get that second red, since I'm holding on to one of the reds, there'll be 1 less red, so that'll be 6 out of, I'm holding on to one of the marbles, 21. Okay, so there's an example of of adjusting our probabilities based on them being dependent of each other. In other words, we don't have replacement in this case. Again, multiplying those through, we can just go 7 divided by 22 times 6 divided by 21. And when I do that, I end up with a 0.09 for my probability. All right, last one here, just another example, pulling out 2 marbles in a row without replacement that are both not red. So we could call that P of not red and red. So in this case, we could have one red or the other red. We just don't want them both to not be red. And the trick with this, what we can do is instead of finding all the different ways we could get 2 marbles that are both not red, what I can do is I can just take a 1 for the probability of anything happening and minusing the probability of it being red, that 0.09, which will give us a 0.91. Okay, moral of the story here is that in a lot of cases we're looking for the probability that something does not happen. It's easier to find the probability that it happens and then just subtract that from 1. Next thing we're going to talk about is probability of multiple events with the OR case, which will be adding. First thing we need to distinguish between is mutually exclusive events. Those will be two events that cannot occur at the same time. So if A and B are mutually exclusive events, then the probability of A or B happening will just be the probability of A plus the probability of B. Otherwise, if they're not mutually exclusive, if they can happen at the same time, P of A or B will equal to P of A plus B of B minus the probability that they both happen at the same time. And really what this subtraction will do is kind of eliminate the stuff we count twice. So let's take a look at a few of the OR cases. Okay, problem 8 says a standard deck of cards has 52 cards, numbered 2 through 10, with a jack, queen, king, and ace in each of 4 suits: hearts, diamonds, clubs, and spades. All right, so standard deck. All right, find each probability. First one, probability of being dealt an ace or a king. I could write that as P of A or K. All right, now, since I can't have both an ace and a king at the same time, okay, they're different values, those will be mutually exclusive. So my answer is just going to be the P of, we could say A for getting an ace, plus the probability of getting a king, so P of K, which will be equal to, there are 4 aces out of the 52, okay, plus 4 kings out of the 52. Okay, so essentially it's just the probability of one thing or the other. Add those two together, my calculator gives me a 0.15, or about 15% of the time we'll get an ace or a king. All right, B, probability of being dealt a king or spade. So P of K, or can we do that? Yep, we can just say S. Now in this case, a king and a spade are not mutually exclusive. A king and a spade can happen at the same time. In other words, the king of spades. So the adjustment we'll make is we'll say P of getting a king again, plus the probability of getting a spade, and then we'll subtract is P of a king and a spade. So there are 4 kings out of the 52, plus there are 13 spades. If we divide 52 by 4, we end up with 13. And then what we have to do for this one is subtract the kings and the spades, in other words, the king of spades. So minus 1 over 52. We have to account for that one that got counted twice when we counted up the kings and the spades. Now when I plug that all in my calculator, I end up with a 0.31, we could say. So 31% of the time we'll get a king or a spade. All right, last problem is a nice little combination of the and the or case. Okay, probability of being dealt a 2-card hand with an ace and a king. Okay, so we could say P of ace and king. Whoops, we'll make that into a D. P of A and K. Well, that's going to be equal to the probability of getting an ace and a king. So that'd just be P of A times P of K. Now in a 2-card hand, the card I'm holding on to is going to affect the probability of the next card. So we'll say this is a P prime. Okay, these two events are not independent. And where the or comes into play is I can get an ace and a king, or I could get a king and an ace. So we'll write that as P of K times P prime of A. Okay, because there's 2 ways for me to get that hand. The order doesn't matter. So aces would be 4 out of 52. Okay, times there's 4 kings out of the 51 remaining cards. Again, if I'm holding on to an ace, I'll have to take one of the cards away from the deck. Okay, plus same thing for probably in a king, that'd be 4 out of 52 times 4 out of 51. And when I multiply that through together on my calculator, I end up with a 0.01. Okay, so in other words, 1% of the time, we'll get an ace and a king. Like we said, we're also going to talk about some statistics in this lesson as well. We'll keep it simple. So here we go. We're going to look at quantitative data, that is numerical values that measure some characteristic of each individual in a set. So for example, let's say I have some numerical values. Those could be test scores, those could be dollars earned per hour of work, okay, really anything like that. And the first thing we're going to talk about are some measures of center. Okay, so how do I figure out what the kind of middle of this data set are? One way could be with the mean, or the average. We'd write that as x bar. That's just equal to the sum of the observations divided by the number of observations. So good old-fashioned average, add up 9 plus 12 plus 17 plus 19 plus 19 plus 21 plus 23 plus 24 plus 24 plus 27. When I do that, I get a 195 on my calculator. And divide that by the number of observations. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can do that in my head. I get a 19.5 for that. Okay, so on average, we'd end up with 19.5. Again, if we're talking test scores, that'd be my average test score. All right, we could also look at instead the median of the data set. Okay, that's just the midpoint of the distribution. Okay, so what's in the middle? Now, advantage of median over mean is, let's say my test scores were out of 100, and I had one student score a 99 on the test. Well, if we're talking about the mean, that's going to make everybody's score look pretty good on average if we add that 99 in there. Okay, the median is not going to be affected by that outlier. That's why you'd want to be able to calculate that. Well, for the mean, what we'll do is we'll just find the middle. There are, like we said, 10 data points. So the middle is going to be halfway between the two of these. And if that middle falls halfway between two numbers, what we'll do is just find the average of those two numbers. 19 plus 21 divided by 2, which would just be a 20. Okay, so in this case, that would be equal to a 20 for this data set here. All right, other thing we could do is talk about which happens the most often, the mode. Now here, notice there's two 19s and there's two 24s. So I'd say my mode is 19 and 24. Okay, if there's more than one mode, we just list them all. Now, if nothing happens more than once, we just say there's no mode. Now, we're also going to look at ways to display our data, and that's going to be one way is with a box plot, where there's a central box is drawn from Q1 to Q3. Now, Q1 stands for quartile 1, and Q3 stands for quartile 3. That's just the middle of the bottom of the top. Okay, so essentially the median of my bottom set of data and top set of data. Okay, well in this case, the middle of the bottom set would just be the 17. So I'd say that Q1 is equal to 17. And the middle of my top set would just be the number in the middle here, 24. Oops, sorry, Q1 is 17, Q3 would be 24. We'd also make a line in the box that marks the median, and then lines extend from the box to highlight the highest and lowest values. Those would be my whiskers if you want to talk about a box and whisker plot. All right, so drawing a box plot for this, what we do is make a number line. And for this one, 9 to 27, we could start at 5 and count by, let's say, 5s. So we could say 5, 10, 15, 20, 25, 30. And again, what we do is make lines for the Q1 and Q3. Q1 is at 17, so we'll say that 17 is about here. And Q3 is the 24, so we'd say here. and there's our box. We'll make a line of the box to represent the median, which is the 20. And then we'll extend the whiskers to the highest and lowest points. We'll extend up to about a 27 and down to a 9. All right, and that's just a rough way we can kind of show our data. Now, we're just going to work on making it. What we really want to do is compare multiple sets of data together. These are great tools for that. We'll just go through how to make that box and whisker plot. Now, in the next problem, we're going to show you how to do the same types of stuff, but how to utilize the calculator, okay, to make the calculations happen. So let's say for problem line, listed below shows the number of Snapchat messages sent by students in Mr. Bailey's first hour over the last 24 hours. So for example, one student entered 0, one student had 0, another student had 0. Okay, the highest was in 118. Okay, that's how many snaps students sent. And I could make those calculations by hand just like I did a few minutes ago, but we're going to want to utilize the calculator for that. So what I can do is go to the Stat button, as in Statistics, and click on Edit, and that's going to pull up a list. And notice what I did here is I already entered those values into this list here, just so you don't have to watch me do that. Okay, everything except for the, last two. Okay, and entering new values, what we'll do is just scroll to the next part of the table. I still need the 98, so I'll just go 98, enter. And then the 118, hit enter. And once they're all in, I can quit. And then I can hit that Stat button, and if I scroll over one to calculate, we want one variable statistics. And we should automatically be calculating them for list 1. I can just hit enter. Frequency list, I can just hit enter, I don't need that, and then click on calculate. And when I do that, it gives me my mean, which is that X bar. It also gives me the minimum value, the Q1, med for median, Q3, and then the max. Okay, so based on that, I can come up with the mean and median of the distribution. That X bar was just equal to 27.48. We'll just say med for median, which was the 9. Okay, the number in the middle of my distribution. Okay, find the mode. Now, this doesn't show mode anywhere on it. So I actually do have to look at my distribution to figure out which one shows up the most. In this case, it's just a 0. There's 3 of them. And then last thing to do, we want to make a box plot quick, which we can just count by 10. So 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. And remember, my box plot had the median in the middle, which was the 9. I had boxes going to my Q1 and Q3, which calculator is giving me Q1 at 3 and Q3 at 43. I'll just make rough estimates of where those are at. And then the box plot extended down to the minimum, which was at 0, and then the maximum, which we'll say is at 118. There we go. And again, the idea with the box plot is it shows the shape of my distribution. Okay, I'd say with this picture here, we see kind of what the middle amount, the average number of Snapchats are, and that's going to let me have some conversations with these students saying, hey, you're way above average, you're kind of ridiculous with your Snapchats. And last thing we're going to talk about is the idea of a normal distribution or a standard distribution. Okay, that's going to be anytime a data set takes on the bell-shaped curve like this. Now that's going to happen anytime the mean is equal to the median, which is equal to the mode. Okay, so when the average, okay, the numerical average, is the same as the middle, which is the same as the values that happen the most often, we'll get this bell-shaped curve. Now it's a family of curves where the shape is determined by the mean, the x-bar, and its standard deviation, the spread about the mean. X-bar determines where the peak occurs, so here's my x-bar, and then the standard deviation determines the spread, okay, how far spread out it is from the mean, how far the data set is from the mean here. So what I have for problem 10 is asking which normal distribution has the greater mean and standard deviation. Okay, so I have two different curves here, both normally distributed, but next to each other we see one's higher, one's further up, one's more spread out, one's skinnier. First off, for the mean, we could say x bar sub 1 and x bar sub 2, as in the first curve's mean and the second curve's. Well, that just occurs in the middle. And in this case, I'd say that the 2 is higher up the line than the 1. So I know from this picture that x bar sub 2, the second mean, is higher than the first. Okay, second thing is that standard deviation. We had this symbol here. We're not going to get into what that's called because I honestly forget it off the top of my head. Since the first curve is wider, it's more spread out, I'd say it has a greater standard deviation than the second curve. All right, so just an example of kind of how those different values can change the shape of my curve. We'll typically look at one at a time, and here's an example of a couple happening at once. All right, then last thing we're going to deal with is the 68, 95, 99.7 rule for normally distributed graphs. Okay, for any normal distribution, we're going to say that 68% of observations fall within one standard deviation of the mean. So as in 68% of whatever we're talking about are going to be one standard deviation up and one below the mean. Okay, 95% fall within two standard deviations. Okay, so if I take that 68% and split it in half, I get 34 on one side, 34 on the other side. That means from 1 to 2 up will be 13.5, and from 1 to 2 down will be 13.5 as well. And then another 99.7% fall within 3 standard deviations of the mean. Okay, so leaving me with 2.35 between 2 and 3, and another 2.35 between -2 and -3. Okay, where those numbers coming from exactly, we're not going to get into that. That's more of an advanced stats type of discussion. We're just going to give you these numbers and show you some different types of problems we can use to solve with them. All right, so for problem 11, let's say that the height of American males is normally distributed with a mean of 69.5 inches and standard deviation of 2.5. Okay, let's take that information and apply it to our graph here. If the mean's 69.5, that means we have the 69.5 right in the middle here. And if the standard deviation is 2.5, what we'll do is we'll add 2.5 to that up. So that would be a 72 for one standard deviation above the mean. And then same thing, a 74.5 for two standard deviations above. And then adding 2.5 once again for 3, we'd end up with a 77 in inches. Then we can subtract the same way. 69.5 minus 2.5 would give me a 67. Minus 2.5 again would give me a 64.5. And then minus the 2.5 again to give me a 62. All right, so this is kind of how American males are distributed. And then we could ask questions like this. What percentage of American males are between 67 and 74.5 inches? Well, that would be everything between these two lines, so 34 plus another 34 plus a 13.5. Which gives us an 81.5%. Okay, so we were developing some type of product that would fit this range of heights. We know exactly what percentage of the population that product's going to fit. And another type of question we can ask is what's above a certain value or what's below. For B, what percentage of American males are taller than 74.5? Okay, 74.5 is here, so we want to know everything above this line. And what that's going to be equal to is we could take 100% and subtract away the 50 to take care of all this, minus the 34, minus the 13.5, and that's going to give us what remains above the 74.5. Which leaves us with a 2.5% of males above that 74.5. Okay, so in other words, above 2 standard deviations above the mean. All right, that's it for our probability and statistics lesson. Okay, like we said, a lot going on. Again, I don't think any one of those types of problems was all that hard. Okay, there's just kind of a lot of fairly simple problems. Okay, so get going on that Math Excel, get that practice in, make sure you give these problems a shot on your own.